Hello, this is Professor Keen. In my last lecture, which was on the scholium of Newton's Principia, Book 1, I talked about Newton's famous spinning bucket experiment. And this thought experiment that Newton carried out was aimed to prove that there is a such thing as absolute space. And although we cannot discern the existence of absolute space by looking at the linear or straight line motion of objects compared to one another, we can discern the existence of absolute space by looking at rotating objects. That is, if we see an object rotating, we can tell whether it is truly rotating or not by whether or not it stretches, so to speak. So in the spinning bucket experiment, one can determine if water is truly spinning, that is spinning compared to this absolute reference frame, which isn't matter at all, but is the fabric of space itself, you might say. You can tell whether this bucket is truly spinning by whether or not whether the water is truly spinning in the bucket by whether or not the water creeps up the sides of the bucket. If it does, then the water must truly be spinning. If it doesn't, then it's not. I realize this is a bit of a subtle argument and is probably the first time you've come across this, so I'd like to go through one more example to try to explain this to you. Okay, so suppose, for the sake of argument, that you are on the inside of a cylindrical spaceship. So suppose, always done that. Suppose you are inside a cylindrical spaceship and this spaceship is floating through outer space, and you are at the center of the cylindrical ship looking down at two masses that are tethered together by strings. Okay, so I'll draw a picture. So this is going to be this cylindrical chamber. It's not a very aerodynamic spaceship, but there you have it. So this is your cylindrical spaceship. And this is the axis of that cylindrical spaceship. You're out in the middle of outer space, okay? And you are floating here in this spaceship. You're an astronaut after all. There's no gravity around, so you're just kind of floating inside of the ship. You're supposed to be inside, but you're kind of near the ceiling. And you look down, and floating at the center of the ship are two bowling balls. Let's say they're two masses, and they're connected by a scale. That is kind of a spring that is stretchable, and maybe it reads on the scale what force there is pulling these apart, if there is one. Okay? So you're observing two masses tethered together by a spring scale. Spring scale that measures the force between them. Okay. Now let's suppose that there are no windows in the ship, so you can't look outside and see any stars. So no windows. All you can see is you, yourself, and these two masses that are floating in the middle of the ship. Okay. So I want you to consider a couple of hypothetical scenarios. So I'm going to ask two questions. So question one is, let's suppose that you look down at this mass, and you observe these two masses spinning around this axis. So suppose you look down and you observe the two masses spinning around, so orbiting about the drawn axis. So the axis that I've drawn right here. Okay, so you see them, you observe them spinning around. Okay, and you also notice that the scale, that spring scale between them, is stretched. So it's reading some force. Okay, so it's stretched, indicating a force. You know, maybe like 20 pounds or something like that. Now, what would you conclude? Well, you would probably conclude, since it looks like it's spinning, and since there's a force, a stretching force, you would conclude, most likely, so you would conclude, and you would be in agreement with Newton, by the way, so you would conclude, as would Newton, that the masses are truly spinning. They don't just look like they're spinning, but they're truly spinning about this axis. You know that they're truly spinning because there's a force, a stretching force right here that's trying to make them fly apart, kind of like the water creeping up on the sides of the bucket, okay? So that shouldn't be too controversial, okay? But let's suppose something else, or maybe that is controversial, but let me ask you another question. This is another hypothetical question. What if you now looked down at those two masses and you saw them once again spinning about this axis? So again, you observe the two masses spinning about the drawn axis. So that's the same as before. But when you look at the scale, you find that the scale is unstretched, indicating no force. So the scale is unstretched. There's no tension in it. So indicating zero force or zero tension in that string. What do you conclude? So it looks to you like it's spinning around, but there's no force kind of trying to pull it apart. Well, what you conclude, along with Newton, is that the masses, first of all, they are spinning relative to you. After all, that's why they look like they're spinning. They're spinning relative to you. They're in relative rotation, but they are not truly spinning. They are not truly spinning. That is, they are at absolute rest, or at rest with respect to absolute space. They are truly at rest. Now, what would that mean? Well, if they look like they're spinning to you, but you know that they are truly at rest, this implies that you must be the one spinning. That you yourself must be truly spinning. After all, if you know by the fact that they're not stretched apart, you know that that thing's not spinning, but it looks like it's spinning compared to you, you must truly be in rotation. That is, rotating compared to this absolute reference frame. So once again, I think this is an experiment, a thought experiment once again, that illustrates exactly what Newton is trying to get at with his notion of absolute and relative motion. Next time, we will go on to chapter 21.